He said electrical fix. Let me refresh.
Just go to the last one and have something call and grab from that.
I just don't see it.
Okay.
Doable.
Oh, you're live.
I'm live. Okay, that's cool. Alrighty, so for those of you joining us online, we had a bit of a hiccup with getting this hooked up with YouTube and streaming it. So we went about through a third of the presentation, and now we are going to restart and commence from the beginning. So welcome to the electrical workshop hosted by RoboJackets. My name is Scott Jansen. I will be hosting this workshop, and I am a FIRST alumni and former member of Team 4026. I did the programming workshop last year, and this is my first crack at the electrical workshop. So with that, let's get started. Let's see, is that, I don't have control of the,
Click the presentation.
hold on. Here we go. Okay, we're going now. So we're going to start out with the power system. The power system consists of the battery, breakers, motor controllers, and anything that it powers, which includes the VRM, the PCM, the RoboRio, everything. Everything is powered by of course, the PDP. So continuing with the PDP. The PDP receives power from the battery and the main breaker. You can see on the sides there are several different sizes of ports. So the ones closest to us are 40 amps and usually handle more higher loads such as motors and motor controllers. And the 30 amp ports usually cover more auxiliary devices such as maybe like a camera, the voltage regulator, which is covered by those ports on the outside there, the top of the screen. Right, so the top of the screen, it provides power to the RoboRio, the voltage regulator, and the pneumatics controller. Those two fuses on either side, the yellow fuse and the red fuse, those are actually pretty standard car fuses, I believe. They don't break often, but most teams don't have them on hand because they don't break that often. So you definitely want to have these two things on hand just in case they do break, because your RoboRio and your VRM will not get power without it, which is very crucial to the robot. On the bottom right-hand side of this image, we have the CAN loop as well as the status lights and the battery terminal for the PDP. And in the middle, that's where the breakers go. So to continue with our note on fuses, what do fuses actually do? Well, they limit the amount of current flowing through a circuit at any point in time. The load determines how much current is drawn. So if you're powering, a motor versus, a little camera, the higher load is going to be the motor, and that's going to draw more current. So you have 8 slots for 40 amp loads, like I was saying in the previous slides, and 8 slots for 30 amp loads. Right, as it says here, the SIM motors and the 775s, 775s are 30 amps, the SIMs are 40 amps. If you're using Falcons, those are going to be 40 amps as well. Generally, any higher power, drive motors. What else? Other motors? Falcons, SIMs. Those are going to be 40 amps. And then one other thing about fuses, they're thermally triggered, and their time to blow depends on the amount of current flowing. So if you're fully powering a Falcon 500, that's going to blow faster than fully powering a SIM. So motors. Neo was the one I left out last slide. Those are also 40 amps. So starting out with brushed, these are going to be your SIMs, Venoms, 775 Redline, bag motors. These are very simple motors in terms of wiring. They don't have any extra control wires. It's just the power and ground. Very inexpensive. You'll find them very cheap nowadays. And then you'll have your brushless motors, which are a bit more complicated. They are better power to weight ratio than brushed, but they require a special motor controller. Usually, these we'll be going over these in the further slides, but these give you a better grasp on control of the motor. You can do more precise things with these motors. The Falcon, the Neo 550. You can do more advanced things with these motors. So the motor controllers that pair with these motors. So brush motor controllers. These are going to be the Talon SRX and the Victor SPX. It looks like we're pretty vague right here, but actually next slide we're going to be going over these features, so stay tuned for those. The Spark are very bare bones, very simple. I don't recommend it, honestly. If you're going to be going with a brush motor controller, the Talon and the Victor pair that's the way you want to go for the CAN integration, the follower mode on the SPX, among other things. For the brushless, you only have one option if you want an external motor controller. That is the Rev Spark Max, which also has CAN integration. And these are going to be if you're powering your Neos mainly. You're going to want the Rev Spark Max. So the features I was speaking about last slide. For the CAN motor controllers, the Talon SRX, the Victor SPX, and the Spark Max, these have special configurable settings that allow you to really precisely control those motors and do more advanced autonomous commands. For example, they have this closed loop control, which they use sensors plugged into the motor controller to accurately control motor properties such as current and speed. So you can really control those in real time to do the maneuvers that you want to do. For the Victor SPX, there is follower mode. So if you have two motor controllers or two motors that want to do a certain action at the same time, you can command a Victor and a Talon to do the same thing. So there are special exceptions to this, of course. One being the Falcon 500, which has an integrated motor controller and an integrated encoder. This is a really great little package. You saw the motor controller. Look at the potential for all those wires going all over your robot, and now you have something like the Falcon 500, which really puts it all together into one package and makes it so that it's very easy to hook this up somewhere and get it going right away. Using these for any use case is wonderful. Drive is probably one of the most common ones I've seen as of recently. And then you have the Venom Smart Motor. I haven't seen much of these, honestly. In fact, I don't think I've ever really seen one, but it is a brush sim motor that I believe it also has a built-in sensor. Not sure which one, but yes, it is a smart motor. So moving on to the control system. This includes any piece of hardware that ultimately goes into controlling the part of the robot, such as the radio for connectivity, the RoboRio for hosting, following the commands and hosting those commands for the autonomous and just directing the robot what to do throughout the match. Cameras, robot signal light, all these things are important to understand what the robot is doing and for our own safety, of course, in terms of the robot signal light. So starting out with the RoboRio, this is what you or your software team will be writing code for. There are a variety of communication options, including USB, PWM, which is there on the right-hand side of your screen. CAN, which this is one endpoint of the CAN loop, and digital I/O, which is on the left-hand side of the screen, that bar. And it also controls the robot signal light, which is important for us humans to understand. What is the robot doing at any given time? Is it disabled? Is it enabled? What is happening? One thing I do want to point out is right there in that bottom picture. There is a special way of wiring the robot signal light. There should be an instructional manual. that comes with the light to show you how to wire it, but it does require a jumper wire between that third port and the first port. So watch out for that. Communications. There are multiple different methods of communication on the RoboRio. Here are 3 of them. So you have digital I/O, which is the simplest version of communication. It can output a 0 or 3.3 volt signal, or read a low or high digital signal, kind of like an Arduino, if you're familiar with that. Very useful for reading simple things like switches or encoders. And then we'll move on to PWM, kind of like the middle ground for communication. Stands for pulse width modulation. It is a series of pulses whose width corresponds to a control value used for motor speed or servo angle. PWM, I would say, they can still be used within robots today, especially for servos, because those don't work over CAN. But it is widely understood that CAN, or controller area network, is the most popular way of communicating between these devices. It is a 2-wire signaling protocol to communicate a variety of information between the RoboRio, motor controllers, the PCM, otherwise known as the pneumatics controller, etc. It also terminates at the PDP. Right, so this is a very popular form of communication, and what I would recommend, if at all possible. So, expanding on the CAN network, all devices that use CAN must be connected together, and that will thus form a network. In FRC, this takes the shape of a daisy chain, so it goes around the robot. It starts at the RoboRio, moves through all of your motor controllers and your pneumatics controller, and ends at the PDP. And as I said, in between you can add any number of motor controllers as you would like. So here is an image without motor controllers, unfortunately, but as you can see, here is on the left is a blown up image of where the wires would go for the CAN protocol at the RoboRio. So right there on the top right-hand corner of the RoboRio is where you put you start the CAN network. It moves through your motor controllers, hits the PCM, and then moves towards the PDP, and that's where it ends. Let's see. You have to set the termination resistor on the PDP block boxed in blue to on. I believe that is enabled by default though, so you should not have to worry about it. But I would check just in case. Let's see, moving on to the router. This is probably, this is like definitely the least up-to-date piece of electronics on this robot. Powering this thing and communicating with it is often a troublesome territory for FRC teams, and unfortunately can't really be remedied that easily. But what it's for is it's used to communicate with the control PC on the field. Basically what you do to power this thing is, first of all, you put a Ethernet cable into the RoboRio. Then with your PoE cable, which is that orange cable, stands for Power over Ethernet, you plug in the other end of that white cable into the PoE cable, just as it says in the top left-hand corner, the image. And then you take that PoE cable, the other end, the male end, and plug it into the radio. And then you take the power and put that in the VRM in that specific spot. It has to be in the 12 volt, 2 amp spot for the radio to work correctly. You may also, the radio does come with like a jack connection. You may also plug that in to reinforce it, but then that means the radio will have 2 methods of power. So I guess that's good for reinforcing it. A quick thing about USB, there are 2 ports in the RoboRio, and they can be used to power devices like cameras and the Raspberry Pis. Very helpful for if you want to do some advanced, advanced autonomous capabilities, or even advanced teleop maneuvers, with the camera or a Raspberry Pi, things like that. So you might have noticed I completely skipped over the PCM and the VRM. Well, I wanted to have a separate section for those because they don't exactly fit in the previous sections. They also provide power, but they're also in the control network. They're standalone devices and need their own section. So the VRM is known as the voltage regulator module. It takes a 12-volt output from the PDP and regulates it to provide applications for smaller devices, such as the router, known as the radio, signal light, Raspberry Pi, and any number of cameras you might want to have on your robot to provide vision. The PCM, this is the pneumatic control module, provides power to all pneumatic devices such as solenoids, the compressor, the pressure switch, and is also part of the CAN loop. If you would like to know more about pneumatics, I would encourage you check out either the mechanical workshop or the controls workshop, which I believe will be going over pneumatics more in detail. So now wiring. Arguably, probably the most, beyond the components, this is, I'd personally say, the most important part of the robot. You will always have problems with your electronics, no matter how great you do your wiring or how poor you do your wiring. You're always going to run into a problem. It could be a breaker blowing up. It could be something gets unplugged during a match. A robot gets on top of another robot and damages the electronics. Something like that could happen. And you always want to ensure that when you're ready to go fix that problem, the origin is clear and you can fix it quickly. So having good wiring is important for that to happen. So before we get started, a little wires 101. So you have stranded wires versus solid core wires. Solid core wires, as you see in the image, have a solid inside, versus the stranded wire has a more, it's the bands can separate and can be twisted, to get a more compact fitting. Then you have the gauge of wires, which is known as the thickness of a wire. It is based on the amount of allowed current in a wire. The higher the gauge, the thinner the wire. And the smaller the gauge, the thicker the wire. So a 12 gauge wire is considerably thicker than an 18 gauge wire, for example. I believe 12 gauge is also the common gauge for things like the motors and those related devices. So connectors. This is something I'm going to emphasize big time because when I was a junior and senior in FRC, my junior year I took over the electrical system and didn't really use these connectors because I know about them. But the electrical that year was okay, but it was a little messy. And then my senior year I discovered these Anderson power pole connectors, and well, they made everything a lot better. If I were the electrical lead of your team, I'd try and get your mentor to buy as many of these as possible that you actually need. Yellow and green ones for your CAN, red and black ones for your motor power and your motor controllers. They just make everything so much easier. Make everything, you don't have to do any soldering. You can just, plug and go and snap them in, and they're just ready to go. It's very, very easy, and also, makes the wires very secure. You don't, soldering is not a very easy thing to do. It's liable to, doing it incorrectly or just simply breaking. But these things are, hard connectors that will not come undone unless shaken by a very hard force. So I highly recommend looking into Anderson power pole because very, very good. So, a little, special device here. It's a drag chain. It keeps wires organized in a very clean way for moving mechanisms. So if you have like an elevator, a turret, things like that, mechanisms that move and require power as they move, using something like a drag chain will be very helpful in keeping your wires organized. This is a very complicated drag chain, but there are definitely more simple models available for FRC teams. So now that we're done with our presentation really for this year, I do want to talk about the 2022-2023 updates and beyond, because there is a lot of changes coming to the electrical system coming in the future, and it is important that you guys understand what is exactly happening, how is it going to work, and what is not legal for this season and beyond. So you might be asking, what's happening? Well, this season, NI, National Instruments, and REV have released the next generation of technology that will be powering FRC robots for the coming years. This involves the RoboRio 2.0, the REV Power Distribution Hub, which is currently being made by Across the Road. Now it's going to be provided by REV. You have the REV Pneumatic Hub and the REV Voltage Regulation Hub. So these things sound very similar to our previous products, which was the voltage regulation module, the pneumatics control module. They sound similar, but are licensed and created by REV now. The RoboRio will still be made by NI. So for 2022, this year, the new REV products will be available for purchase and are competition legal. However, they will not be coming in your kickoff kits due to supply chain shortages. With the chip shortage that's going on worldwide, they will not be able to provide these new products. Instead, Cross the Road products will be in your kits for this year. But both REV and Cross the Road products will be competition legal in 2022. For 2023, the new REV products will be coming in your kickoff kits. First states that Cross the Road products will continue to be legal for the future years. So if you do not want to move on from REV or move on from Cross the Road, you want to stick with Cross the Road, you don't want to do the REV products, they will be legal for future years. So thank you guys for listening, for the three of you in person, for everyone else that is watching virtually. Thank you. Hope you enjoyed and appreciated the presentation. Any questions? Not sure I can actually see the virtual questions unless I pull up the YouTube stream. So,
I'll pull it.
Okay. Thank you. Hope you. Do you three have any questions in the meantime? No.
You don't see anything online right now?
Okay, we can stick around for another 5 minutes and wait for people to come with their questions.
The drag chain, first I had seen that was, that's one of the biggest challenges on getting things organized so nothing catches. I've seen some really great robots that look like somebody threw spaghetti at them.
Yeah, absolutely. Yeah, you can have a fantastic design, but then just absolute spaghetti when it comes to the wiring and other, it's very important.
What kind of connectors do they have?
Well, this is a generic drag chain, but normally what you'd have is just kind of like see the links on the outside. What I believe it's I forget the company that does the IGUS. IGUS is the one that makes they make plastic connectors like this. That the IGUS connector chains, and you can put in your own wires, like yeah, you thread through the 12 gauge wires that you're using, and then you can
Okay, this is a channel for you guys.
Yeah. This is just a dedicated channel.
In the initial slide you had, it looks like they had a wire rack. Everything was sitting on the bottom of the chassis.
Mm-hmm.
That is
It's beautiful. Yeah, absolutely. Yeah, you can see the power pole and the near the motors there. Yeah, it's beautiful. Oh yeah. Absolutely.
so nice.
Absolutely. I do like the material that they're laying all their electrical components on. It allows for like the zip ties to go under.
Good airflow.
Oh yes, nothing overheats.
Yeah, so that is
Very nice.
So I'm trying to look at that. So They've got the motors going to the amps, so I got your 30 and 40 amps, but do they have the CAN, what was it?
The CAN system?
Do they have the CAN system?
They
on the
do.
top left?
See the green and yellow wires that move through the motor controllers, and then you'll see it ends at the Rio there and the.
See the data change on the top, okay.
Yep.
Yeah, I was thinking we had that, but we don't. Just got the regular going to the 30 and 40. So what's the benefit of doing that? Doing the CAN again?
The CAN, it's easier for the motors to be controlled that way, and a lot of the, if you want to use PWM, you can. You just have to get older motor controllers.
'Cause I know that, their daughters are lead programmers, so they'll adjust motor speed for where we're at to shoot and do stuff like that.
Right.
Would that make that easier to do it if you could more control it? Because we do it without that. I mean, she programs it, she speeds it up, slows it down, and for shooting and stuff like that, depends on where we are on the field. Push that button, that one's going to go that far.
I'd say these are the Talons are more helpful for like autonomous, more advanced autonomous commands. I'd say so. You can do teleop commands. Those are relatively. You can do those with any motor controller. Those are going to be mostly the same. But for the Talons, the SRXs, these are going to allow you to have more advanced autonomous routines.
And this year, autonomous, I don't know how much they're going to do autonomous. It didn't look like, just looking at the game, it's just like.
It looks very bare bones.
Yeah, it does. Yeah, so some teams can make them rack up a lot of points. We've seen them do it. How many points did they score on the autonomous?
Yeah.
Do you have a drag chain in this setup right here?
Oh, this one? No, I think it's just the wiring.
It doesn't look like it needs it, because everything, it's going to have something. If you're going to have something on top.
Yeah, this is very much a bare bones chassis. That's.
Just the chassis, so if you got anything on top, which you didn't want. I don't have a lot of sports open.
Yeah, if you have questions about specific Talon SRX features, I'd encourage go checking out the mechanical the programming workshop, because those are the programmers are the ones who really know about the features and functionalities of that Talon SRX. Yep, no problem.
Yeah, you think a lot of teams don't get to the advanced features of Talon, or it's almost like a little computer, right? So if you're very thorough, you can read the Talon data sheet, and they'll be like, the little computer on the Talon can do optionally this big list of things, right? And some teams, most teams don't use most of the features, and some of them still will end up implementing them in software on the Rio because they either want their students to learn or they want more control over the specifics of the implementation, right? So, like we mentioned, the controls workshop was going to talk about PID. We mentioned that the Talons can do PID for you. So PID is a way of compensating for error, right? So if you say, I want the motor to go, 6 rotations per minute, and you command 4 motors to go 6 rotations per minute, and you see one is going like 6.1, one's going 5.8, you're like, why is that happening, right? It's like, this is like mechanical differences that stack up into doing stuff like that, right? It manifests itself as well when you're trying to go over longer distances, that error builds up. So those controllers have something called PID to help correct for that error. And you have to go through, and there's like a process where you can say, I'm going to set all these constants that kind of correct for these variations. So that's going to be different per motor, right? Different error, different constants to correct somewhat, at least, is something we typically see, right? Depending on how well you want that error corrected. But, if you mention like PWM is very simple, it's just a one-wire signal out, right? It's not capable of communicating that density of information to have those complex features. So you won't get stuff like that at all, period, over PWM. You have to use a CAN-enabled controller, at least in the FRC world, if you want to start exploring that stuff. Now, some people find that super frustrating, and they don't like to use Talon's PID. There's nothing preventing you from learning what it is, writing the PID algorithm on the Rio, and then having the Rio do all of that for all of your motors, and then just sending the raw corrected output
To the PWM.
That's also still totally valid. Like my team used to do it the manual way because we wanted the control over it. Talons didn't exist yet, but they were just starting to get there, and they weren't like documented as great. We're just like, we don't like this. So, we never used them in CAN mode, but it's getting more popular as more people are doing it. There's more resources. It makes more sense. I mean, you don't have to spend the time writing it yourself. Don't, right?
If folks, because we haven't never used this, but we figured out Swerve Drive. We're using Swerve Drive. Would you probably want to use the CAN to be able to do that? But each wheel, or each wheel has its own code from what I understand. We've never used it, but it's just, you see them go there extremely fast.
Yeah, usually the ones where the wheels, they're like a motor that swings them, not something like Mecanum, right?
Exactly.
Yeah.
Swerve Drive, I think is what it's called.
Yeah, so again, it's sort of totally up to you. I think either approach can be valid for Swerve. I think Swerve is more complicated, like period, and so you may find that those features become more necessary. But in terms of whether you want the motor controller to do it or you want to work with software to have them implement some of it themselves, I think you could be successful either way.
The few times we've talked to teams about it, it seemed like the software intense when they were doing it. So they're exploring that avenue versus having the motor controller. But there's only so much time you have to.
Right, yeah,
Exactly.
6 weeks.
Yeah.
Very short.
Yeah.
It's one of those things where I don't know exactly what FIRST provides from a software standpoint in terms of how easy it is to set and use those motor controllers. But that is an area where you could get electrical and software to work together, and software can maybe provide or write a library for their team, or perhaps share with other teams that makes using that controller a little bit easier, independent of whatever the year's game is, right? Try to reuse that season to season. If you have the bandwidth to build up that sort of institutional knowledge, I know that's frequently not the case, right? But this is probably getting a little bit pedantic, but the one thing that can be a little wonky about CAN is because it is a chain. You have to be very diligent about securing that wire, because if you break the chain, you don't just lose one bit of function.
You lose all the follow.
You break the whole thing,
Yeah.
right? Which is interesting, and it's a big reason that automotive connectors and wires are as ludicrously expensive. You look at it, they get this like big fat metal connector, and you're like, why would anyone pay money for that? It's like, well, the automotive industry uses it, so they may have 50 sensors change through it. So if one of those breaks, they're like real unhappy. So just a thing to be mindful of, right? Is if you're going to go the CAN route, try to secure your CAN chain best if you can.
For sure.
Because robots tend to run into things too. Or other robots run into things.
Oh, yeah.
So, that's what we were talking about earlier, thing of the soldering. How many times has a solder broken?